SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe. You can download SpaceTime as a free twice-weekly podcast just about everywhere, including iTunes, Stitcher, Pocket Casts, Bytes.com, YouTube, SoundCloud, Audio Boom, and from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C. Coming up on SpaceTime, the most detailed ever map of the universe, a new gravitational wave research centre, and X-rays detected streaming from Pluto. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
The largest ever all-sky celestial survey has published its first catalogue, pinning down the exact three-dimensional positions and brightness of over 1 billion stars. The data from the European Space Agency's Gaia spacecraft will form part of the most detailed map of the Milky Way ever created. This initial catalogue covers some 1,142,000,000 stars, including the proper motions across the sky of over 2 million stars. The Gaia spacecraft, launched in 2013 on a 5-year mission, is at the forefront of astrometry, charting the sky with a level of precision never previously achieved. Its data will revolutionise our understanding of how stars are distributed and move across the galaxy. Gaia started its scientific work in July 2014, and this first release is based on data collected during its first 14 months of scanning the sky up till September 2015. This new map shows the density of stars measured by Gaia across the entire sky. In addition to processing the full billion-plus star catalogue, astronomers also looked in detail at roughly 2 million stars in common between Gaia's first year of observations and the earlier Hipparcos and Tycho II catalogues, both derived from ESA's Hipparcos mission, which charted the sky for more than 2 decades. By combining the Gaia data with information from these less precise catalogues, it was possible to start disentangling the effects of parallax and proper motion, even from only the first year of observations. Parallax is a small motion in the apparent position of a star caused by Earth's yearly revolution around the Sun, and is dependent on the star's distance from us. On the other hand, proper motion is due to the physical movement of stars through the galaxy. In this way, scientists were able to estimate distances and motions for 2 million stars spread across the sky in the combined Tycho-Gaia astrometric solution. This new catalogue is twice as precise and contains almost 20 times as many stars as the previous definitive reference for astrometry, the Hipparcos catalogue. As part of their work in validating the catalogue, astronomers conducted a detailed study of open stellar clusters. These are groups of young stars that were all born together. With Hipparcos, astronomers could only analyse the three-dimensional structure and dynamics of stars in the Hyades, the nearest open cluster to the Sun, and measure distances for about 80 clusters up to 1,600 light-years away. In contrast, Gaia's first data allowed scientists to measure distances and motions of stars in some 400 clusters up to 4,800 light-years away. For the closest 14 open clusters, the new data reveals many stars surprisingly far from the centre of their parent cluster. They're likely escaping the cluster to populate other regions of the galaxy. The new stellar census also contains 3,194 variable stars, that is, stars that rhythmically swell and shrink in size, leading to regular periodic brightness changes. Many of the variables seen by Gaia are in the Large Magellanic Cloud, a satellite dwarf galaxy to our own Milky Way, and a region that was scanned repeatedly during the first month of observations, allowing astronomers to gain accurate measurements of these variables' changing brightness. Details about the brightness variations in these stars, 386 of which are new discoveries, are included in the catalogue. Variable stars like Cepheids and RR Lyras are important because they're used as standard candle cosmic distance markers. While parallax can be used to measure distances to large samples of stars within the Milky Way directly, variable stars provide the next larger step in determining galactic distances. This is possible because some kinds of variable stars, such as Cepheid variables, change in brightness at set rates linked to their mass. So, by knowing the star's mass and how intrinsically luminous it really is, astronomers can then determine how far away it really is because of how bright it looks to us. The same is true for RR Lyras, which are observed in infrared light. Their variability pattern's easy to measure and can be combined with the apparent brightness of the star to infer its true brightness. And this is where Gaia steps in. In future, scientists will be able to determine very accurate distances to a large sample of variable stars, all thanks to the Gaia measurements. Astronomers are still coming to terms with the scientific implications arising from the historic first-ever detections of gravitational waves. Over the past year, teams working with the Advanced Laser Interferometer Gravitational Wave Observatories, or LIGO, in Louisiana and Washington state, have confirmed 2 definite and 1 possible detection of gravitational waves, ripples in the very fabric of space-time, caused by the movement of extremely dense massive objects, such as black holes and neutron stars. On September the 14th last year, LIGO successfully detected its first ever distortions in space-time, caused by passing gravitational waves generated by 2 black holes colliding nearly 1.3 billion light-years away. The historic signal, named GW150914, was caused by the merging of a 36 solar mass and a 29 solar mass black hole, resulting in the formation of a new 64 solar mass black hole, with a mass equivalent of our Sun converted to pure gravitational energy. A second gravitational wave detection was made on December the 26th last year. That signal, named GW151226, was caused by the collision of a 14 solar mass and a 7.5 solar mass black hole some 1.4 billion light-years away. A third weaker signal had also been detected but not confirmed on October the 12th, 2015, possibly from another black hole merger. These detections have opened up a new window in our understanding of the universe. Gravitational waves were first predicted by Albert Einstein in his 1915 theory of general relativity, which describes how gravity is the effect mass has on the fabric of space-time, causing it to warp and distort. Einstein showed that massive accelerating objects, such as neutron stars or black holes orbiting each other, distort both space and time, emitting a new type of radiation known as gravitational waves. And that's where LIGO comes in. The Laser Interferometer Gravitational Wave Observatory comprises 2 4-kilometre-long arms, forming a right angle. A laser beam, split in 2, is fired down each of the arms. The beams then reflect off mirrors at the ends of the arms, returning to a special detector. Now, if the return beams don't match up exactly as expected, it means a passing gravitational wave has caused a microscopically small squeezing and stretching of space-time somewhere along the path of the laser beam. This contraction and expansion is smaller than the diameter of the nucleus of an atom, and it's hidden deep inside a dense background of quantum noise. Australia had been in the forefront of gravitational wave research thanks to facilities like the Gingin Gravitational Wave Research Centre, operated by the University of Western Australia. However, the Gillard government turned down an offer by the United States to set up a LIGO facility in Australia. As a direct result of that decision, that LIGO facility is now instead being built in India. That means Australian research into gravitational waves will, for the moment at least, focus on developing new subsystems and tests for observatories in other countries, and it'll also look at new ways to analyse the data they produce. As part of these efforts, the Australian Research Council has provided $31.3 million in federal funding for a new Centre for Excellence at Swinburne University, which will study gravitational waves to better understand the extreme physics of black holes and warped space-time. The new facility, to be called Ausgrav, will open next year. It'll research issues such as the accuracy of general relativity theory when applied to the most extreme gravitational forces, and what other astronomical objects are likely to generate observable gravitational waves. Ausgrav will also explore whether supermassive black holes merge often enough to allow astronomers to see their death cries with telescopes like the Square Kilometre Array, which is now being built in Australia and South Africa. And it will research if general relativity theory can be used to determine neutron star masses in order to help define the equation of state of nuclear matter, which is derived from a known dependence of energy per particle of a system on particle number density. Ausgrav Director Professor Matthew Bales says the centre will allow scientists to improve the sensitivity of LIGO and to develop new technologies like quantum squeezing, which will further enhance the detectors.
Astronomers, or scientists maybe more accurately, have been developing the instrumentation to detect gravitational waves for some 40 years now, and it's remarkable technology that really pushes the boundaries of engineering. the distortions in space-time that we can detect are mind-boggling. It's equivalent to a change of the width of a human hair at the distance to the nearest star, which is a phenomenal technology. And it allows us to probe gravity at the kind of intensity that is impossible here on Earth.
And this will help with not just studying black holes, because the two confirmed and the one possible gravitational wave detection so far announced by the LIGO team have all involved merging black holes. And this will also look at neutron stars, things like that.
Yeah, so there's two properties that have to occur. One is they need to rotate at the right frequency for LIGO to be sensitive to it. So that really restricts you to neutron stars and black holes. White dwarfs are also a very compact and dense form of matter by human standards, but they can't get close enough to each other to radiate in what they call the LIGO band. So LIGO is only sensitive to certain frequencies, and it's really tuned for neutron stars and black holes. I think one of the amazing things was the black holes were completely unexpected. We knew how many neutron stars there are in the universe because we've discovered pulsars and we know how often they appear in pairs, but we really had no idea of how many black holes there were going around other black holes. And so it was quite a shock that the first event were these two black holes. Nobody had ever discovered a black hole much bigger than 10 solar masses on the sort of stellar scale. And finding that black holes were actually a dominant channel was a really great shock.
And the fact that these were intermediate-sized black holes too. These were the really rare ones that we've sort of been looking for because they're too big to be, conventional stellar black holes and too small to be supermassive.
Yeah, we really had no detection mechanism for such black holes unless we were lucky enough to catch them when they were being shone on by a companion star. That appears to be reasonably rare. And you can think of these black holes as sort of time bombs out in the universe waiting to go off. And you've got to be watching at the right time, which is billions of years after they actually coalesce, to see them coalesce. And we just really didn't know how to explore the universe for black holes like that until advanced LIGO turned on.
A lot of people are saying that what they're actually seeing with this are possibly even population 3 stars that have converted to black holes and have been reasonably isolated, so they've sort of maintained their existing size until such time as they finally merge.
Yeah, it's thought that when a star's metallicity gets too high, it can't actually create a black hole that's 30 solar masses. It'll blow away more material than is going to be left to form the black hole. So it is a possible way of looking back at the universe when the very first stars were being formed, but that's pretty conjectural at the moment. I think we need to find more of these things to learn about where they came from and whether they're these remnants from population 3 stars or something more common, or whether they're actually created in the cores of globular clusters, which could be breeding grounds for such systems.
How long was advanced LIGO going for during the test run? It was, just a couple of months, wasn't it?
I think the overall kind of what we call integration time was a few months. It doesn't actually work kind of 24/7. It has to maintain lock. It's quite a challenging thing. So I think that it works roughly half the sort of calendar time.
It's got to take into account things like passing trains and heavy trucks and anything else that could affect the delicacy of its lasers and mirrors.
Yes, so achieving what they call lock is quite a challenging thing. And maintaining it is also challenging. And there's certainly dead times when, because of external vibrations or earth tremors or whatever, you've got no hope of having any sensitivity to inspiring black holes. But on the whole, people are absolutely delighted with the results of the first run, and they're now getting ready for the second major run, trying to tune a little bit better, see a little bit further out in the universe. And part of Ozgrav's program is to make advanced LIGO the best detector it can be by contributing something called quantum squeezing, which could, in fact, sort of double its range, which would be fantastic.
How does quantum squeezing work?
The uncertainty principle kind of puts a limit on how good your detector can be, but it turns out you can play quite a clever trick where you sacrifice knowledge of the amplitude of a wave in order to get a better understanding of the phase of the wave. That's about as far as I understand it at the moment. Our partners at ANU are world leaders in this, and they're leading the program to implement quantum squeezing from Australia into advanced LIGO.
Now, your focus will be on the computer technology, won't it?
Well, we have three themes within Osgrove. We have an experimental theme headed by David McClelland at ANU, and then we have a data theme, which I'm leading from Swinburne University, and we also have an astrophysics theme that Yuri Levin, the gravitational wave theorist from Monash University, is leading, and there's going to be close cooperation between those three themes of Osgrove.
And part of all that involves a new computer, which will come online next year?
Yeah, so we're currently designing the next supercomputer at Swinburne University, and we're hoping to get a copy, if you like, of all of the LIGO data and really use it as a focus for the world to do some of the computations to search not just for inspiraling black holes and neutron stars, but also what they call continuous wave sources. This is looking to see if you can see minute deviations from a sphere of rotating nearby millisecond pulsars. It's possible that there's a gravitational wave strain continually being stretched and squeezed as the gravitational waves from the neutron stars pass, but unfortunately you can't measure that in seconds. You have to integrate your data for more like years to have a chance of seeing something like that.
A couple of years ago, we were offered a spare LIGO interferometer. They had 3 over there. They only needed 2. And so they offered us one of theirs. That was not accepted, and that's now gone to India. Do we need one in the Southern Hemisphere?
Well, one in the Southern Hemisphere is advantageous. Having another one anywhere is certainly very important, because ruling out chance coincidences between 3 detectors is a hell of a lot better than 2. If you try and work out what's the positional error, on a gravitational wave source, if you only have 2 detectors, it's really a very large, like 1,000 square degrees. That's about a 40th of all the sky. So it's a bit like saying it occurred somewhere in the universe. If you can get a 3rd detector, you can knock that down to sort of tens of degrees, depending on how intense the signal is and its wavelength, if you like, how rapidly it was being generated. The neutron stars are a little bit easier to pinpoint than the black holes because the frequency at coalescence is a little bit higher. It turns out that where the current LIGO detectors are, if you had one in Australia, it's better than India. It's not like it's a factor of 100 times better. It's a factor of a few. And all of these factors help when you're trying to do science.
One of the important things that LIGO will do, when it detects a gravitational wave, it provides a trigger for optical and radio telescopes to start looking for the same source. And if we had a better way of targeting where that was by having additional detectors, then that would make that job much quicker.
Yes, and I think everybody agrees that the time between the event and when you can get on sky is crucial. So one of the things we'll be doing in Osgrove is trying to accelerate or minimise the time between the event happening and its detection. So Lin Chin Wen from UWA has a very fast code that actually works on computer games cards, and she'll be using that in Osgrove to try and minimise that time so that telescopes can see. It doesn't always help you if it's the daytime when the event happens at your particular continent.
Yeah,
but
true.
luckily radio waves don't care what time of day it is, and some of Australia's investment in things like the SKA are going to be fantastically well timed for Osgrove, because we'll be able to use things like ASCAP and SKA low and SKA mid to see if there's any radio embers that we can see to help us pinpoint the sources of gravitational waves.
This could be useful for the square kilometre array to also find sources.
Yeah, what we're finding more and more in astronomy is a lot of these instruments end up working together. They work in concert to try and maximise the science. And many of us are now kind of multi-wavelength astronomers. Gravitational waves is a little bit different, and it's not a different wavelength. It's a completely new transmission mechanism. And it has some advantages over radio and optical in that gravitational waves can travel through anything unimpeded. It has a disadvantage at the moment. The positional localization is not wonderful, but it will improve when the European detectors turn on and Japanese detectors, and hopefully ultimately we can plan to have an Australian detector.
In the short time Advanced LIGO was running, it picked up 2 confirmed, 1 possible gravitational wave detection. That means at least 1 a month, we could assume. They say that possibly once the technology is more advanced, we could be looking at 1 a day.
Yeah, that's not a crazy number. The range to neutron star coalescences at the moment is of order 75 megaparsecs. That's about 200 million light years. By the time Advanced LIGO's had all the sort of sources of noise eliminated and things like quantum squeezing added and better isolation and so on, we might get another factor of 2.5 in distance, but that's a factor of 2.5 cubed in rate. So that's quite exciting. If you sort of multiply out those numbers, then you're you're nearing the kind of one every few days.
It's a decent slice of the universe too.
Yeah, I think the joy of the black hole mergers is that we saw them a lot further away than we thought we'd see anything. And we just had no idea that 30 solar mass black holes even existed. We know they exist, and I'm sure they're not the most exciting thing we're going to find over the next 7 years of Ozgrav's existence.
That's Professor Matthew Bales from Swinburne University's ARC Centre of Excellence for Gravitational Wave Discovery. Astronomers using NASA's Chandra Space Telescope have detected X-rays streaming out of the distant world of Pluto. The discovery, reported in the journal Icarus, indicates that Pluto's atmosphere is interacting with the solar wind in an unexpected and energetic fashion. The solar wind is the constant stream of charged particles generated by the Sun. The new findings offer fresh insights into the space environment surrounding Pluto, the largest and best-known Kuiper Belt object in the outer reaches of the solar system. The Kuiper Belt is a ring of small frozen worlds, comets and icy debris circling the Sun beyond the orbit of Neptune. The belt extends out from the orbit of Neptune at roughly 30 astronomical units out to around 50 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres. Pluto's highly elliptical orbit ranges over roughly the same distance span. While NASA's New Horizons spacecraft was speeding past Pluto, Chandra's X-ray telescope was aimed towards the dwarf planet and its moons, gathering data to compare with the New Horizons flyby. Each of the 4 times Chandra pointed at Pluto between February 2014 and August 2015, it detected low-energy X-rays emitting from the dwarf planet. The findings are surprising given that Pluto, being cold, rocky and without a magnetic field, has no natural mechanism for emitting X-rays. However, scientists had previously also detected X-rays being generated by a comet. So the New Horizons scientists were especially interested in learning more about the interaction between the gases in Pluto's atmosphere and the solar wind. The research team are using the data to develop a picture of Pluto that contains a very mild close-in bow shock where the solar wind first meets Pluto and a small wake or tail behind the dwarf planet. It's all very comet-like. Mind you, the story doesn't end there. There's a more immediate mystery, namely that Chandra's readings on the brightness of these X-rays are far higher than expected from the solar wind interacting with Pluto's atmosphere. The Chandra detection is especially surprising since New Horizons discovered that Pluto's atmosphere was far more stable than the rapidly escaping comet-like atmosphere that many scientists had predicted before the spacecraft's flyby in July 2015. In fact, New Horizons found that Pluto's interaction with the solar wind is much more like the interaction of the solar wind with Mars than with a comet. However, although Pluto is releasing enough gas from its atmosphere to make the observed X-rays, models for the intensity of the solar wind at the distance of Pluto indicate that there isn't enough solar wind flowing directly onto Pluto to make them. Astronomers think the enhanced X-ray emissions could be caused by a much wider and longer tail of gases trailing Pluto than what New Horizons detected. Other possibilities include interplanetary magnetic fields, which could be focusing more particles than expected from the solar wind into the region around Pluto. On the other hand, it could be that the low density of the solar wind in the outer solar system at the distance of Pluto may well allow for the formation of a donut or torus of neutral gas centered around Pluto's orbit. New Horizons has an opportunity to test these findings and shed more light on this distant region of the outer solar system during its extended mission to encounter another small Kuiper Belt object, 2014 MU69. That encounter is slated to take place on January 1st, 2019. While it's unlikely to be feasible to detect X-rays from MU69, Chandra might be able to detect them from other larger and closer objects that New Horizons will observe as it flies through the Kuiper Belt towards MU69. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, and from SpaceTimeWithStuartGary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C.
This is SpaceTime with Stuart Gary. For more, you can follow us on Facebook, Twitter and Tumblr. Just search for SpaceTime with Stuart Gary.
SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine. This month, looking at whether the next generation of supercomputers will be able to handle the mega streams of data expected from the next generation of giant telescopes like the Square Kilometre Array.